Hello everyone, I am Sadia Sharmin from Islamic University of Technology, Bangladesh. I am going to present this paper, Discretization and Feature Selection based on bias-corrected mutual information considering high-order dependencies. Due to the presence of high-dimensional dataset, feature selection is now playing an important role in pattern recognition and data mining. It is important to find out the most relevant features from the dataset for improving the classification performance with low computational cost. Discretization is also important for classification, which is applied before feature selection to transform the continuous valued feature into discrete ones. Usually, feature selection methods can be divided into three categories: filter, wrapper, and embedded. Filter methods are mostly popular as they are classifier independent and thus work faster. In filter methods, different criteria are used to evaluate the performance of a feature. In our work, we have focused on mutual information based filter methods as they can capture the nonlinear relationship between variables. In mutual information based methods, the problem is to select a subset of features that will maximize the joint mutual information with the class variable. Also, the value of this mutual information changes depending on its discretization level. So we need to find the way of selecting feature subset with their proper discretization value so that the joint mutual information is maximized. However, calculation of this joint mutual information is a NP-hard problem. Addressing these issues, different approximations have been proposed in the existing literature. For example, MRMR method proposed an equivalence of joint mutual information by maximizing the feature relevancy with the class variable and minimizing its redundancy with the selected features. Here, relevancy represents the mutual information between a feature and a class, whereas redundancy is measured by calculating mutual information between two feature variables. In GMI, an additional term called complementary is present. Complementary term represents the correlation of the features within classes which can provide useful information for classification while maximized. In Relux MRMR, the authors consider high-order feature interaction term for their approximation along with the relevancy, redundancy, and complementary term. However, all these methods we have discussed are feature ranking method and cannot choose the proper discretization value. In addition, when mutual information is being calculated for finite number of samples, there exists some error. None of these methods has considered this error in their work. Addressing these issues, in our previous work, we have calculated the bias value for relevancy, redundancy, and complementary term and propose MDSM that can discretize and select features simultaneously. But you can see that the interaction term used in Relux MRMR is not present in MDSM. Considering this issue, our first contribution of this paper is to derive the bias value for interaction term theoretically and propose a new selection criteria called JDSBM. The second contribution of our work is to incorporate this DSBM criteria in chi-square searching. For that, we have proved that the interaction term follows chi-square distribution. Now, combining this selection criteria and searching strategy, we propose a new feature selection method called DSBM, which can simultaneously discretize and select the features. However, the chi-square searching of DSBM is a forward selection process, where a feature once selected cannot be deleted later. Solving this problem, we have proposed another method called DSBM-FP with a new searching criteria that is chi-square based simultaneous forward and backward elimination search. Now we'll describe the process of our proposed method. Let's see how DSBM works. For example, we have a set of n features. For each feature, we'll calculate the relevance value with minimum discretization level for which the relevance passes its corresponding chi-critical value. We'll get a set of candidate features. Now the features will be sorted based on their relevance value in descending order. The first rank feature of this list is the most relevant features, so we'll include it to the final selected subset. Now the second one will be the next candidate feature for evaluation. We'll calculate the gain of this feature using JDSBM criteria and check whether it passes the critical value. If so, we'll include this feature to the selected subset. During this process, the discretization value of the candidate feature is also shifted by a small value. In this manner, all the features will be evaluated. If any feature doesn't passes the condition, then it will be discarded. Continuing this process, finally get the selected feature subset. But in DSBM, we cannot delete a feature from the final selected subset. However, it may happen that more informative features can be discovered later for which we need to remove features from the selected subset. This blue circle represents the total information of a selected feature subset can provide about the classes. The orange and the yellow circle represent the information of another two selected features. And as we can see that they have increased the overall information area of the selected feature subset. In this phase, when a new candidate feature X is considered for selection, it will not be selected as it is mostly redundant with the selected feature subset. But observing carefully, we find that the feature X alone can provide the extra information that A and B have combinedly added to the selected subset. In this case, backward elimination is required for improving the searching process. With this motivation, we have introduced DSBM FB with a new searching mechanism considering backward elimination. So when a feature doesn't passes the critical value, we'll further consider whether it is more informative compared to the already selected feature. For this, we calculate the three-way interaction value of the candidate feature with the selected ones. From all possible combinations, we take the features with the maximum interaction value and check whether the candidate feature can increase the gain significantly by replacing the less informative features. If so, we will replace the selected feature with the candidate one. If the gain doesn't increase, we will not process the backward elimination. In this process, DSBM selects the final feature subset. Here's the details of our experimental setup. This table represents the average classification accuracy of tenfold cross-validation using support vector machine. We have summarized this table here in terms of pairwise win-tie loss. For example, DSBM has 13 wins, 3 ties and 4 losses in comparison with MDSM. We have also shown the significant win-loss by performing t-test. The last row shows the average number of selected features, and we find that DSBM selects less number of features compared to other methods. As JMI and Relux MRMR is feature ranking method, the number of selected feature is as same to DSBM. Overall, DSBM outperforms the existing state-of-the-art methods. In this table, we have represents the result using k nearest neighbor. K nearest neighbor DSBM also achieve higher accuracy for most of the dataset. We have used another metric, Pareto optimality. It returns the set of non-dominant methods that outperform other methods for both accuracy and number of selected features. We can see that DSBM has appeared in the Pareto optimal set for most of the cases and thus got the highest rank. We also perform Friedman tests to determine which methods perform significantly better than others considering both accuracy and number of selected features. It shows that DSBM also beats other methods in the ranking. Now we compare DSBM with DSBM FB. Find that DSBM FB can achieve similar accuracy with less number of selected features due to the backward elimination process. In this result analysis, we can conclude that our proposed method can select a better subset of feature, and we can use this method in different applications such as activity recognition and biological data analysis. However, this proposed bias correction in DSBM only works for large sample dataset. In future, we'll address how to calculate the bias value for a small sample dataset. Thank you everyone for listening to my presentation.